Today we're going to look at another way of finding derivatives called the chain rule. So before we do that, I want to review some notation from algebra. So this is a function kind of within a function. We call this f of g of x. Okay, so it involves what we call composition of functions. So this is just a way to combine functions by putting one function inside another or plugging one function inside another. Okay, so just before we get started on the derivative part, if you had f of x was x squared plus 1, and then you had g of x were square root of x, and then what if I told you to find f of g of x? So again, this is review from algebra. So with composition of functions, you always start from the inside, so you always start with the inside function, which in this case is g of x. So you would be finding f of the square root of x. So in other words, now this means go to your f equation and replace the x's with what's in the parentheses. So instead of x squared plus 1, we have square root of x squared plus 1. Okay. Notice these are opposite operations, so the square root of x squared is just plain old x. So f of g of x is x plus 1. It's important to note that most of the time these will give you different results, unless they happen to be inverses, but we're not really talking about that today. So again, you start on the inside function. This time the inside function is f of x, so we're finding g of x squared plus 1. So that means go to your g equation and replace x with what's in the parentheses. So in the end, we don't really need this set of parentheses, and we just get the square root of x squared plus 1. Notice no simplification can be done here because we don't know what x is, and x squared and 1 are not like terms. So think of the chain rule as the way we deal with functions like I just showed you here. The chain rule is the method for finding derivatives of composition functions or composite functions. So far we've only been able to do the basic form of any of the types of functions we've been looking at. And so I like to just say this, these are for more complicated looking functions. Alright, so we're going to look at chain rule and then kind of how chain rule interacts with some of the rules we already know. So if I want to find the derivative of g of f of x, then that derivative is going to be the derivative of the outside function, okay, evaluated at the inside function. We're going to do some examples, so don't freak out yet, times the derivative of the inside function. Okay, so like before, I'm going to rewrite this in everyday words. So this is basically what we're doing. We're doing the derivative of the outside function evaluated at the inside function. Okay, but essentially for short, we're just going to say it's the derivative of the outside function times the derivative of the inside function. So I'm going to abbreviate here so I can fit it on one line. In other words, we're going to do the derivative of the outside times the derivative of the inside. That's essentially what the chain rule is. So let's look at a rule that before test 1 we discussed quite a bit. So we've talked about the power rule a lot, right? That's where we move the power out to the front and we reduce the power by 1. The general power rule is going to be similar, but it's going to be for when you're raising more complicated functions than maybe just a plain old x. Notice we're raising f of x to the n power. So we will still do the power rule, which says move the power out to the front and reduce the power by 1. But then we will also multiply that by the derivative of the inside function. Okay, so this is how I kind of like to explain these. It's the derivative of the outside, meaning move the power to the front and reduce the power by 1, and then times the derivative of the inside. So what it's going to allow us to do is just open up lots of different types of problems that we can find the derivative of that we wouldn't have been able to easily do before. So let's take this first example. Okay, notice we only know how to do things like x to the 5th power, not a parentheses to the 5th power. Okay, that requires the chain rule. So notice I have an inside piece, it's in parentheses, right? And then I have something to the 5th power. So the derivative is going to be the derivative of the outside. So let's talk about what the outside is. The outside operation is that we're raising it to the 5 power. So we're going to move that power out to the front, keep the parentheses the same, and reduce the power by 1. Okay, this is essentially like the derivative of the outside. And then we're going to multiply that by the derivative of the parentheses itself, the inside function. Okay, so the derivative of 2x plus 4 is just 2. I'm spacing that out so I can label that appropriately. So this is the derivative of the inside. So notice we're just really kind of multiplying by a constant there in this case. So we'll get 10 times 2x plus 4 and then to the 4th power. Okay, don't forget we're still doing derivatives, so this is still the equation of the slope of the tangent. Okay, so instead of doing plain old x to the 5th, we're going to be doing things like a parentheses to the 5th power. Okay, so that's kind of the difference in the problems that we're doing today. Okay, so it's going to really open up the door for us to be able to do all kinds of things that we wouldn't have been able to do before. So remember back a few sections ago we learned how to take the derivative of an e to the x power function, but we couldn't do anything other than just plain old e to the x. Well, now we can with chain rule. Okay, so the derivative of e is always itself. Okay, so think of this as the derivative of the outside. But then, because we have something other than x, we have to do chain rule as our exponent. So now we're going to do times the derivative of the inside meaning the exponent in this case. So the derivative of x squared plus 1 is just 2x. And notice this is the derivative of the inside. So in the end, usually you would rewrite this like this, 2x times and then e to that power. Usually we write ln and e terms last. Okay, it's not technically wrong to change the order, but because this has an exponent, it just looks nicer like this. Okay, so notice I'm going over kind of all of our old rules kind of mixed with this new chain rule. Okay, so remember back a while ago when we were asked to find the derivative of the ln of x, it was always 1 over x. Well, when you have the ln of something more complicated, it's 1 over whatever happens to be on the inside. And then it's going to be times the derivative of that inside. So this is like the derivative of the outside. And then we're going to multiply by the derivative of the inside. So the derivative of x to the 4th is going to be 4x cubed. So this is the derivative of the inside. So in the end here, we end up getting 4x cubed on top, and then x to the 4th plus 1 on bottom. Okay. You can't simplify that anymore because there's not x's in everything, so don't try to cancel out the x's or do anything weird like that. You're not allowed to do that. All right, so we're just going to do a few examples until you kind of get the feel of what chain rule looks like. Remember, chain rule is for what I like to call more complicated looking functions. So what if h of x is x to the fourth plus 1 to the negative 2 power? So on the one hand, we have something to the negative 2 power, so that requires that we use power rule. But on the other hand, it's something more complicated than just plain old x to the negative 2 power, right? So enter chain rule. So chain rule says do the derivative of the outside. In other words, move the power to the front and reduce the power by 1 first. Okay, so this right here is the derivative of the outside. But then because we have something more complicated than just plain old x, then we also have to do times the derivative of the inside. The derivative of x to the fourth plus 1 is just 4x cubed. So this is the derivative of the inside. So in the end, if you clean everything up, if I multiply the negative 2 times this stuff, I'll get negative 8x to the third, and then over x to the fourth plus 1 parentheses cubed. Notice I move that to the bottom, again, because we don't want to see negative exponents. Okay, so what about this one? Find the derivative if f of x is equal to 1 plus natural log of x, and then that whole thing cubed. Okay, so certainly a more complicated function, right? We have something that kind of looks like a pane, right? And then we have it cubed. So don't forget to state, hey, I'm about to take the derivative. So on the one hand, we have a power rule, so we're just going to do that. So move the power out to the front and reduce the power by 1. Notice, I don't change what's in the parentheses in this step. Okay, all I do is move the power to the front, reduce the power by 1. But then I do have to multiply by the derivative of the inside. So let's talk about that. The derivative of 1 would be 0, right? It's just a constant. The derivative of the natural log of x would be 1 over x. So this is the derivative of the inside. So if you work this out, you're just going to get the 3 times the parentheses 1 plus ln of x squared on top, and then the x on bottom. Okay, so we're really just kind of doing a lot of examples here. I'm just trying to kind of mix in all of our old formats in with this new chain rule. So d dx of that cube root function. So notice it's not just the cube root of x, right? It is the cube root of a mess, right? A long function. So the first thing before we start, let's rewrite this just like we would before. This is the same as saying the derivative of x to the fourth plus 3x, and since it's cube root, it's to the 1/3 power. So if I want to find the derivative, notice since I'm using this notation, I don't have to say f prime of x, okay? But I would move that power out to the front. I would keep what's inside the parentheses the same, right? And if I subtract 1 from the power, be careful there. 1/3 minus 1 would be negative 2/3. So this is only half of the answer. This is just the derivative of the outside, in other words, the power rule in this case. And then I still have to multiply by the derivative of the inside. Okay, so what would be the derivative of what's inside the parentheses? 4x cubed, right? Plus 3. Okay, so make sure if it has more than one part, you have to put parentheses around it. So in the end, let's decide what goes on top. This 4x cubed plus 3 goes on top. And then this 3, and then that parentheses raised to the negative 2/3 moves on the bottom because of that negative exponent. So in the end, that's what you get there. So I'm really not going to teach you any more rules. I'm really just trying to see how this new rule interacts with some of the old rules that we should know well by now. So if g prime of x, find g prime of x, sorry, if g of x equals x squared and then e to the 3x. Okay. Notice what I said a while back. If you can find two things with x in them, they are two separate functions. So x squared is its own function, e to the 3x is its own function. Notice, even though we don't have a multiplication dot, we're going to need to use product rule here because we're multiplying x squared times the e to the 3x. So let's just remind ourselves what product rule is, right? It's first, use parentheses, times derivative of the second. So we need to be careful here. The derivative of e is going to always be itself. But then because we have something other than just e to the x, now you're going to multiply by the derivative of the exponent as well. So this is first. This is derivative of the second. So we're halfway there. Now we do plus the second times the derivative of the first. Really important that you use parentheses. Maybe not for this one in particular, but in general, you'll want to get in the habit of using parentheses. So I just put a parentheses around kind of every separate part. So I would be okay with this answer, 3x squared e to the 3x plus 2x e to the 3x. But your MyMathLab online is probably going to notice, hey, these have at least an x in common and an e to the 3x. So if you were to factor out an x and an e to the 3x, here you would have left 3x. Here you would only have left 2. So I'm just going to say or there. So I think MyMathLab takes either. It's just that if you look at the help features, which I know a lot of you are really prone to do, it's probably going to give you this form, but honestly, I'm okay with this form. Okay, so, but if you want to look at what the help features has, usually they like to factor out what they have in common. All right, so what about one where we use the product rule? So what about one where we have to use the quotient rule? So I wouldn't say we ever love to use the quotient rule. The quotient rule is probably one of our more tedious formulas, right? But in this case, we don't have a choice. We're dividing, so quotient rule is definitely the way to go. So again, hopefully you remember this. But remember the formula for quotient rule. Use parentheses. Bottom times derivative of the top. So here's where chain rule comes in. The derivative of e is always itself, but when the power is not just x, you also have to multiply by the derivative of the exponent itself. So that's bottom times derivative of the top minus the top times the derivative of the bottom, and then all over the bottom squared. Okay, just like I've said so many times before, we usually don't mess with the bottom, but we can simplify the top. So we have some distributive property here. So let's go ahead and write what we get. So we're going to get, if we do this times that, we'll get 2x squared e to the 2x plus 18 e to the 2x. So 9 times 2 is 18, right? And then minus 2x e to the 2x. And then all over the denominator squared. So I would be okay with this, but again, MyMathLab is going to say, hey, these all have something in common. They have at least a 2 in common, and they have that e thing in common. So if you were to pull 2 e to the 2x out, here you would have left x squared. Here you would have left 9. Here you would have left x. So MyMathLab in help features, again, is probably going to give you something more like the second piece, but I'm okay with this first form here. just as long as you know the rule. All right, so let's just do one more like this, and then we're going to apply it to some of our application problems, again, that we've done in the past. So what if I wanted you to find the derivative of this little number? Okay, so notice we're using dw instead of ddx, right? Because w is the letter we're using here. So notice, before I start, let's rewrite it. Always, always rewrite fractions, okay, if you want to use the power rule anyway. So notice, this would just be w squared minus 6 to the negative 5 power. Okay, I can use brackets if I want to there. So it's 5 because that's what I was given, right? It's negative 5 because of where it's located. It's located on the bottom. So no need for f prime because I'm using that dw notation instead. So remember, power rule. Move the power out to the front and reduce the power by 1. Okay, remember with negative numbers, if you subtract 1, you're going to get a larger negative number. This is only half of chain rule, though. This is the derivative of what I would call the outside piece. And then I still need to do the derivative of the inside. So the inside is the parentheses, right? So what's the derivative of the parentheses? Just 2w, right? So this would be the derivative of the inside. So let's see if we can clean this up and move things where they should go. Negative 5 times 2w is negative 10w. And then this thing moves to the bottom because of the negative exponent. Okay, so these are going to take some practice. Okay, they're a little more complicated functions, but just remember, we need chain rule for questions where it's not just plain old x. Maybe it's not just e to the x, or maybe it's not just x squared. It's like a parentheses squared or something like that. Okay, just kind of a heads up. I want you to think about maybe one of our old problems. Okay, if I told you to find the derivative of x to the 10th power using chain rule. Now, by the way, you don't need chain rule to do these, to do this one in particular. So let's make that f of x. Okay, you don't really need chain rule because it's just plain old x, but let's just pretend that we didn't know that. If I wanted to find the derivative, I would do the derivative of the outside. So what does that mean? Move the power out to the front, reduce the power by 1, and then I would multiply by the derivative of the inside. Well, the derivative of x is just 1, right? So I end up just getting 10x to the 9th. In other words, we could do chain rule all the time. It's just it's not necessary to do chain rule when the inside piece is strictly x, because the derivative of that inside piece would always just be 1. Okay, so that's just kind of a goofy problem to look at, really, but notice we really can't mess it up. So if you're in doubt, should I use chain rule or should I not, the answer is you should, and if you really didn't need it, you're just going to get a 1 when you multiply by the derivative of the inside, which of course doesn't change anything. All right, so let's do a few application problems. So the look of these shouldn't be foreign to you. It's just that we're going to need our new chain rule to be able to do pieces of it. So find f prime of x in the equation for the tangent line of f of x equals x, and then 4 minus x cubed at x equals 2. Okay, so first let's find the derivative. Okay, so before we do that, we do need to recognize, hey, I actually have product rule going on here because I have two pieces that have x in them. So my formula is first, right, times derivative of the second. That's going to be the tough part. Okay, we're going to put that in parentheses. So the derivative of this guy says move the power to the front, reduce the power by 1. but then also multiply by the derivative of the inside parentheses, which the derivative of 4 minus x is just -1. So notice, kind of lengthy on that part, right? This is the first. This is the derivative of the second. And we still have half of it to go, right? Plus the second times the derivative of the first. The derivative of x is just 1. So now let's just clean this up. So we're going to get -3x, right? So I'm doing x times 3 times -1, and then we have 4 minus x squared. Don't do distributive property if you have a power other than 1. Okay, so we'll just leave that alone. And then notice we'll get plus 4 minus x cubed here. Okay, my math lab might write this a little bit differently, but I'm okay with this form. So notice that's part of what I was asked for. This is also the equation for the slope. So from here on out, this is just like problems that we've already done before. So from here on out, I just need to find the slope. And why do I need to find the slope? Because I need to use this formula. So this should definitely ring a bell for you, right? We've been using y minus y1 equals m times x minus x1 a couple of times. So remember what you need for that, right? We need a slope. We need a point. Okay, so how can we find the slope? Well, we have an equation for that, right? So to find the slope, I just need to do f prime of the x value I was given, which in this case is 2. So -3 times 2 times 4 minus 2 parentheses squared plus 4 minus 2 parentheses cubed. So just let your calculator do all of that, okay? But you'll get -16, so I'm going to circle that. So notice we have a point, now we need we have a slope, excuse me, now we need a point, right? So we have the x part of the point, but we need to find the y. Okay, and you always find the y by plugging in the x you were given into the original. Okay, so y is going to be f of 2. So we'll just plug it in just like it looks. 2 times parentheses 4 minus 2 cubed. So the y value you'll get is 16. So the point that we need then is 2, 16. And now we are ready to do our slope formula, right? Or a point slope. Y minus the y value equals m times x minus the x value. And then if you work all of that out, you'll get, sorry, and I messed that up, right? X minus the x value is actually 2. And if you distribute and move stuff around, you'll get this right here. Okay, so the only new thing here is really just this part, okay? Finding the derivative formula. Past that, we've really done that before, right? We've done plenty of y minus y1 equals m times x minus x1 problems. All right, so let's look at another one. Find f prime of x and find the values of x that make the tangent line horizontal. So hopefully that last little phrase you recognize. Okay, so when the tangent line is horizontal, remember that means the slope is 0. So I guess I need to give you f of x, right? That would probably be helpful. So f of x in this case is x over 2x plus 5 parentheses squared. So anytime we're asked to find tangent line, we need to find derivative first, right? Which we were already told to do that anyway. So we're just going to go kind of slow here. So remember, quotient rule is bottom times derivative of the top. Derivative of the top is just 1 minus the top times the derivative of the bottom. So here's the tricky part, right? Chain rule. Move the power out to the front, reduce the power by 1, but then also multiply by the derivative of the inside. This is certainly the toughest piece here. And then don't forget to put all of that over the bottom squared. Now, if something squared gets squared again, then it's just going to be to the 4th power. Okay, so if you square something twice, you'll get to the 4th power. So let's try to clean this up. So notice 1 times this, we're just still going to get this, right? So we're going to work that out maybe in a minute. Here, we're going to get minus 4x, right? 2 times 2 times x, and then times 2x plus 5. And then over 2x plus 5 to the 4th. Alright, so we are going to have to simplify this. So we get 2x plus 5 times itself. There's a couple of ways we can simplify this. I'm going to go with the most mainstream one. So we're going to FOIL this guy right here. So you're going to get 4x squared plus 10x plus another 10x plus 25. And then I can do distributive property here, right? Remember I said don't do distributive property if the power is something other than 1, but here the power is 1. So it's going to be 4x squared, or minus 4x squared rather. And then, just kidding, right? Minus 8x squared. Sorry about that, 4 times 2. And then minus 4x times 5 is a minus 20x. All over the bottom squared, well, which makes it to the 4th power. So let's combine like terms. Okay, so notice 4x take away 8x is negative 4x squared. But notice 10x plus 10x minus 20x actually is gone, right? It goes away. And then I get plus 25. And then over 2x plus 5 to the 4th. So I know I said normally we leave the bottom alone, and that's true. Okay, normally we do leave the bottom alone, but there are some 2x plus 5s that we can cancel. So honestly, on a test, I would probably be okay with this, but I know my math lab's going to want you to simplify that. So let's just talk about this one. If we factor out a negative, we're going to get 4x squared minus 25, and then over 2x plus 5 to the 4th. But hopefully you recognize this as a difference of 2 squares. Okay, in other words, 2 things being subtracted from each other that are squares. So this comes out to be 2x plus 5, 2x minus 5 if we factor it. The reason that's significant is because notice that matches up with something we have on the bottom. Okay, so we're allowed to get rid of this and then get rid of one of those, leaving 3, right? So in the end, we get negative 1 times 2x minus 5, and then over 2x plus 5 to the 3rd power. So if my math lab is telling you your answer is correct, but it's not fully simplified, you probably need to do something like this. Okay, so now notice what we need to do. Now you need to set the derivative equal to 0 because we're trying to find, remember originally, where the tangent is equal to 0. So for a fraction problem, algebraically, we just need to set the numerator equal to 0, because if the top is 0, the whole thing is 0. So set the numerator equal to 0. And if you solve, I'm going to let you kind of do the algebra there, you'll get 5 over 2. Okay, so the values of x that make the tangent line horizontal is 5 over 2. All right, and then last but not least for this lesson, let's look at maybe a business application. So let's say total cost for a cell phone distributor for X cell phones is C of X equals 10 plus the square root of 2x plus 16. And let's say this is only valid for X is in between 0 and 50. And C of X is in hundreds. So X represents cell phones, C of X represents the cost in hundreds. Okay, so I'm going to ask you to do a couple of things with this. First, I want you to find the derivative. So before we do that, let's rewrite C of X. So we could rewrite C of X as 10 plus 2x plus 16 to the 1/2. And notice we'll want to, right? Because if we're going to find derivative, we want to make sure we have it as an exponent. So C prime of X is going to be, the derivative of 10 is 0. So now let's do the hard part. Move the power out to the front. Reduce the power by 1. But then we still need to multiply by the derivative of the inside because this is just the derivative of the outside. So the derivative of the inside is, in this case, 2. So when we go to simplify this, notice that 1/2 times 2 is just 1. So you're just going to get 1 and then 2x plus 16 to the 1/2 on the bottom, 1 over that quantity. Okay. Remember, we also can rewrite this as 1 over the square root of the 2x plus 16, however you want to say it. Both of these are correct, as long as we don't have negative exponents. All right, so what if I told you to find some specific values? C prime of 24 and C prime of 42, and interpret the results. Interpret the results just means briefly tell me what the results stand for or what they mean. Don't just give me a number. Show me that you understand what that number is. Okay, so let's start with C prime of 24. So I'm going to use this format. I think it's easier to talk about. So it's 1 over the square root of 2 times 24 plus 16. So if you use a calculator, this actually comes out somewhat pleasantly. It comes out to be 1 over the square root of 64, but that's 1/8, or 1/8. Just don't forget that this is in hundreds. In other words, you actually need to do 1/8 times 100 if you're not sure. So you end up getting 12.5 for an answer. And remember, this is the derivative of the cost. So this is what this means. Cost is increasing. It's increasing because the derivative is positive. It's increasing by $12.50 per unit, or in this case, per cell phone, when 24 cell phones are produced. So the rate of change for the cost, or the total cost, when we're producing 24 cell phones is $12.50. So the cost is increasing. Okay, so let's do the other one. C prime of 42 would be the same equation, right, but plug in 42. And this one actually comes out nice too. It's 1 over the square root of 100, which is 1/10. But again, that's in hundreds. Okay, so if you need to, 1/10 of 100 is just 10, right? 1/10 times 100 is just 10. So what does this mean here? That means the cost is increasing by only $10 a cell phone at this level of production, right? When 42 cell phones are produced. So remember when we talked about marginal cost? So the marginal cost is less at the higher level of production than it is at the lower level of production, okay, at least for the numbers we chose. So the total cost is still increasing in both cases, but it's increasing by less here than it is here.